Okay, folks, let's dive back in. You are now in the final project era of the course, and during this era, at the first few minutes of every lecture, I will take a few moments to offer up tips and tricks, field questions if folks have questions they want to ask. Just as a reminder, as I mentioned last time, you're working on your final project idea, and if you haven't already, if you're coming up with your own final project idea, please see myself or the TA to make sure we can help you calibrate expectations about what's doable over the next 4 or 5 weeks or so. You're trying to then break your final project idea down into 4 bite-sized chunks, 4 weekly deliverables, the first of which is due at next Monday at 11:59 p.m. Okay. Some of you are still finishing up with assignment 9 and 10, and I tried to get everyone oriented last time about how to go about debugging your system if it's not working, and I realized I misspoke last time. I talked about search.py and generate.py. Generate.py has been retired, right? There's just solution.py. There's just solution now. So search.py writes out all the information that simulate.py needs. Simulate.py needs to compute the fitness of a given robot that's encoded in a genome. Does this sound more familiar? Okay, all right. Apologize for misspeaking last time. As I mentioned, if this is still not working, you can make a few changes to search.py so that when it runs, it will run and write out G, and then it will exit or die or terminate prematurely. So you can alter search.py so it spits out one genome. You can go in and inspect all the files that should be written out, which is the environment file, the body file, and the brain file. Make sure all 3 of them are there, and that simulate.py can read them all in and delete them, and then write out F, and then simulate itself ends after computing fitness. So part of the reason why we've developed your final project into these 2 processes is so that you can pull them apart and dissect and debug each one on its own. Yeah? Okay. Any questions about any of that? Okay, as you're thinking about your final project and how to break it down into 4 weekly deliverables, most of you are going to start to think about different fitness functions for your robot. So it's important to us that you communicate that fitness function clearly to the TA and myself, but most importantly to yourself. So I would invite you, if you haven't already, to start to use a little bit of math to figure out your fitness function. We talked last time about a hypothetical fitness function for a jumping robot. So how do we create a fitness function that gets the robot off the air and keeps the robot in the air for as long as possible? We talked verbally last class about maximizing the number of time steps at which the touch sensors are reporting -1, that they're not in contact with anything. Okay, how do we represent this mathematically? We could describe T as the touch sensor value, and we could then add some subscripts to index into this. So the touch sensors, remember that in the quadruped there are 4 touch sensors, and each of those 4 touch sensors is either firing or not firing at each and every time step. So we could add to T here 2 subscripts. Subscript I is going to represent the ith touch sensor, where I is going to range over 1 through 4, and J is going to represent the time step at which we're looking at that touch sensor value. So when you're writing this up for yourself and then for the TA and myself, I would suggest you try and write down your fitness function or maybe other aspects of what you have in mind. If you can write it down mathematically, please do so because it makes things very clear. Okay. This is not an evaluable function because we haven't defined I and J yet. All we've done is introduce a little bit of notation, which is this particular scalar, this particular floating point number represents the value of the ith touch sensor at the jth time step. What happens if we want to sum up all of the touch sensor values over every time step. How do we represent that mathematically?
Summation.
Okay, you all remember this? Okay, summation, what do we need up here? What do we need down here? What do we need up here?
If I equals 0, j equals 0.
Let's say I comma j, so both of them are going to start at 0, and then
So like n, like how many?
typically would use uppercase N, where uppercase N is going to represent.
The amount of robots.
It could be the number of robots. Actually, that's a great point. So if we have a swarm, we might have a third subscript. This is the value of the ith touch sensor at the jth time step inside the kth robot, right? So depending on what you're doing, you're going to develop a little bit of notation and then a little bit of math to show us what you have in mind. So for example, actually let me simplify this a little bit. Let's have two summations. We're going to sum up over all the 4 touch sensors in the quadruped, and we're also going to sum up over all of those touch sensors at every time step. So in the inner case here, we're going to have I equals 0 through 3, because we've got 4 touch sensors in the robot, and then j equals 0, and that's got to run to uppercase T, which is the total number of time steps you're going to run your simulation for. So now the TA and myself, and hopefully you, can look at this and say, okay, if you were to run the evolutionary algorithm that you have at the end of assignment 10 on the quadruped, and you use this as the fitness function, what do you expect the quadruped is going to do when the evolutionary algorithm ends for this fitness function? You all running this simulation in your head, this evolutionary algorithm in your head? We run the evolutionary algorithm. Robots that get a low value of f are thrown away, and robots that get a higher value of f are retained and produce randomly modified copies of themselves. What do we get at the end? What are we evolving this robot to do?
Isn't the touch sensor value equal to 1 when it's on the ground? So it would just...
This value is equal to 1 when that touch sensor is in contact with the ground. And this value is minus 1 when that touch sensor is not in contact with the ground. So
It would stay on the ground.
it would evolve to stop moving, right? Hopefully your quadrupeds are doing something like this when they're equipped in generation 0 with random sets of synaptic weights. This fitness function, if you plug this in, should evolve robots that exhibit less and less motion and keep all 4 feet on the ground at all times. Yeah. We talked last time about trying to keep as many feet off the ground for as much as possible. Yeah. So one of the things you could do in the rest of this week and into the weekend, as you're starting to think about ideas, you have a code base now, hopefully you have a code base now that's working where you can easily plug in different fitness functions and sort of see what happens. This is a form of debugging where you're debugging your ideas about how to apply evolutionary selection pressure. Biologists talk about selection pressure. These are evolutionary processes. In your case, it's your genetic algorithm or your parallel hill climber that is pushing the population towards larger and larger values of f. So you can plug in different mathematical expressions and see the evolutionary process start to push the robot in different directions. If you plug this in and you evolve it and you get something other than a robot that is robots that are increasingly in contact with the ground for more and more time, something is wrong with your evolutionary algorithm somewhere, or your assumptions about what your code is doing is wrong. This is a higher level form of debugging. Okay, this is also a good exercise to perform every once in a while, again, just to build up your intuition about your code base. We talked about this last time. Hard to hold this relatively large code base in your head now. try different things and see that it comports with your expectations or your predictions. I predict if I use this, the robot will stop moving and stay in contact with the ground. If I put this fitness function, I expect that I'm going to see robots that are increasingly tap dancing as evolutionary time proceeds. Yeah? Okay. Any questions about any of that? Any questions about the final project in general? No? Okay, back to lucky lecture 13 here, which is taking us a little while to get through, but that's okay. There's a lot going on in lecture 13. We're going to conclude lecture 13 today, which is our discussion of the NEAT algorithm, and we're going to end that discussion in a moment and complete a discussion of sort of a sequel algorithm. This is another very popular algorithm still used today in evolutionary robotics and other branches of AI called HyperNEAT. That will finish lecture 13. We're a little bit behind where I'd like to be at this point in the semester, so we're going to go very quickly through lecture 14, which is a shorter lecture. Lecture 14, we're going to look at, it's a short lecture with a very long title. We're going to look at the very first attempt, the very first algorithm that tried to take evolved robots from simulation and bring them into reality. This was known as the radical envelope of noise method or hypothesis. Hopefully we'll finish that today and move on to the second attempt to bring evolved robots from simulation to reality, or the second attempt to try and cross the reality gap, which became known in retrospect as the Golem project, and we'll see why in a moment. Okay, so back to lecture 13. We ended last time with a deep dive into the heart of the NEAT algorithm and what the NEAT algorithm was designed to do, which is to cut two parent neural networks and glue their parts together to produce a child neural network that is similar, looks similar to its parents, which you can see here, and hopefully behaves similar to its parents. So if this parent is kind of pretty good at computing exclusive OR, and this second parent is also pretty good at computing exclusive OR, but maybe in a slightly different way, this child should also be pretty good at computing exclusive OR. If you take two machines and cut them in half and glue them together, as you can imagine, most of the time it's unlikely that that new machine is going to do what the parental machines do. If I grab a Mac that's in this room and cut it in half, and I grab a tablet that's in this room and cut it in half and glue them together, probably I'm not going to get a very fast, workable machine. It's a tricky thing to do, to take complicated, partly working machines and put them together so you get a machine that not only works, but hopefully sometimes you, by chance, happen to bring good bits of parent one together with other different good parts of parent two. Yeah. I'm not going to go through all this again about how this works. You'll have to trust me that that's what NEAT does. So when you implement NEAT or run the NEAT algorithm, you're evolving populations of neural networks. Over time, those neural networks get better at F. They get better at whatever you want the machines to do. And usually those machines, if F is difficult enough, if the task you want the neural network to do is difficult enough, the internals or the guts of these neural networks start to evolve sub-solutions to your problem. Whatever the solution is to your problem, it's usually a composition of sub-problems. In this evolving population of neural networks, different neural networks are getting better at different sub-problems in different parts of their guts. And it turns out that the NEAT algorithm, every once in a while, it will grab two survivors. Those become the two parents. NEAT will cut those two parents in the way I described last time and glue the bits together. And every once in a while, it'll bring together the good bits of both parents. NEAT will, from time to time, cut a Mac in half and cut a PC in half, but cut them together, to cut them apart in very careful ways. It doesn't bring both CPUs from the Mac and the PC into the new machine, and doesn't fail to bring one of the hard drives into the new machine. It manages to copy exactly one copy of each necessary part into a child, and you often end up with a child neural network in the evolving population that looks and acts similarly to both parents, and because it inherits good parts from both, gets a higher fitness than either parent. Yeah? As we saw last time, it takes quite a bit of algorithmic machinery to get all of this work to work, but it does. For some of you that feel relatively comfortable with your programming expertise, you might want to try and tackle implementing the NEAT algorithm in your final project. Okay. All right, so we talked about what it's designed to do and how it does it last time. Any questions about NEAT before we move on to HyperNEAT? No? Okay. Okay. HyperNEAT, as the name implies, is an algorithm that has NEAT at its core. So HyperNEAT is a pretty complicated algorithm. We've just seen NEAT, which is algorithmically complex. Relax. All of these algorithms ultimately are evolving populations of things against a fitness function. Throw away things in your population that have low F and make randomly modified copies of things that have higher F. That's what NEAT does, as we just saw. It evolves populations of neural networks. HyperNEAT also evolves populations of things, but it evolves those things in a particular way. It evolves these solutions, as we'll see in a moment, in a way that biases the evolutionary search towards things that have repeating structure. So here's my little cartoon insect. If you look at an insect, it's made up of a bunch of parts that repeat themselves. The HyperNEAT algorithm tends to evolve things that have symmetry. So my little cartoon fly here and you are bilaterally symmetric. The left side of your body looks more or less like the right side of your body, at least on the outside. If we were to dissect you and look at your nervous system is not a random collection of 10 to the 11 neurons and a random ball of spaghetti of 10 to the 14 synaptic connections. There is regular structure throughout your central nervous system and your peripheral nervous system. Across your body and brain, there is repetition, regularity, symmetry. Why? Why aren't we just a random collection of things? I know it seems like a silly question, but when you think about it, why not? Why are you bilaterally symmetric? Recall our discussion of bipedal locomotion. Why aren't you bilaterally asymmetric? Okay, if you're asymmetric, so you take a big heavy knapsack and put it on one side, you can maintain balance. It's a little bit more difficult. Why? You can make yourself bilaterally asymmetric.
Or it would just like take more energy.
Takes more energy. So passive dynamic walking or hybrid dynamic walking, which is what we do, we spent a lot of time talking about that last week. It works because it's very energy efficient. And it works because we are bilaterally symmetric. You can still walk if you're bilaterally asymmetric, and we're back to the Ministry of Silly Walks, but it takes more energy to do so. There are good reasons for why various aspects of our physiology is symmetric, why there's repeated structure, and so on. You've probably already seen this in assignment 10 at this point, which is when you start the quadruped, which is bilaterally symmetric. The left side of the quadruped looks like the right side of the quadruped. It's also radially symmetric, like a jellyfish. As you go around in a circle, each bit around the circle looks like every other bit. The physiology of the quadruped is symmetric, but in the first generation of controllers for your quadruped, its brain is not symmetric. Assume a simple Bratenberg vehicle with 2 sensor neurons and 2 motor neurons. If the 2 weights of these synapses are this brain is not bilaterally symmetric. The way signals flow from this sensor to this motor is different from the way signals flow from this sensor to this motor. So at the beginning of A10, when you start evolving controllers for your quadruped, its body is symmetric, its brain is not. What kind of behavior do you tend to get in the first generation? What behaviors do you observe for your quadruped when it's being controlled by an asymmetric neural controller? Likes to turn around in circles, tap dance. Its behavior is also not symmetric. For those of you that have evolved the quadruped for long enough, you might notice that the evolutionary algorithm tends to clean up the gait and it starts to walk with a more regular pattern. But it often takes a while, 10, 20, 30, 50 generations, and depending on your laptop, a few minutes, a few hours to do it. Your evolutionary algorithm is spending a lot of time exploring asymmetric brains before it starts to find regular patterns and symmetry within the synaptic weights of the neural network controller for your quadruped so that it starts to move in a regular way. So far, so good? Questions, comments, anything's unclear? Okay, seems horribly inefficient. I forget how many synapses there are in the quadruped, but however many there are, we have that length vector. And your parallel hill climber or genetic algorithm is searching over the space of all possible vectors of floats of that length. As I mentioned last time, that space is more or less infinite. The parallel hill climber is moving out across a fitness landscape that is very high dimensional. The vast majority of vectors in that space produce asymmetric controllers. Make sense? Even for my simple Bratenberg vehicle here that had just 2 synapses, the number of vectors in which both floating point numbers are exactly the same, that's a vanishingly small minority of all the vectors of length 2, of floating point vectors of length 2. So wouldn't it be great if we could make an evolutionary algorithm that avoids the vast majority of asymmetric solutions to whatever your problem is and focuses its evolutionary search just on symmetric patterns, patterns that repeat, and so on? How would we go about doing that? That's exactly what HyperNEAT is designed to do. HyperNEAT is going to search over the space of neural networks, but it's going to focus its effort on patterns of synaptic weights that repeat across the neural network or are symmetric. And we're going to see at the end of this lecture that ends up helping the evolutionary algorithm. The evolutionary algorithm is able to increase F faster because it's moving through a part of the space. That contains regular repeating patterns in the solution. That's the intuition. So far, so good? Okay, so how does HyperNEAT do that? It does this in kind of an odd way. Let's see how it does that. HyperNEAT does this by evolving neural networks. Here's one of them over here. In this case, we have 2 input neurons, 3 hidden neurons, and 1 output neuron. But this neural network operates in a slightly different way from what we've seen before. What this neural network is going to do itself is paint a regular pattern onto something else. Seems a little odd. Let's start by seeing how these neural networks work. We're going to decide that we want this neural network to paint a pattern for a moment into a 2-dimensional space. We haven't said much about what this thing is yet. We're just going to make this thing paint patterns. I forgot to mention these neural networks have a very specific name. They're called CPPNs. It's a bit of a clunky acronym here. Let's focus on the PPN for a moment. pattern producing networks. This is arguably one of the very first Gen AIs there were. This is a generative AI. It was published back in 2009. It's going to generate or paint a pattern onto something else. And it's going to do it using a composition, but we'll come back to that in a moment. Let's imagine we're going to task this CPPN with painting colors onto a 2D canvas. So 2D, we've got an x-axis and a y-axis. Let's assume we have this particular CPPN over here, this particular network. What we're going to do is in our canvas, we're going to visit a regular number of points in this space. We're going to visit x equals 0, y equals 0. Then we're going to visit x equals 0.1, x equals 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1. And then y equals 0.1, x equals 0, x equals 0, 1, 0.1, 0.2, 0.3. We're going to walk through this canvas. And at every point, we're going to take the coordinates of that point. We're going to take the 2D coordinates of that point, which at the beginning, the first time we do this, is going to be 0, 0. We take those two values and plug it into the two input neurons. So what is the input to a CPPN? The input to a CPPN are coordinates. We're going to feed in 0, 0 here. And I want you to just forget the internals of this neural network for a moment. You'll notice that this neural network has one output neuron. So that output neuron is going to receive, after these values propagate down to the output layer, they're going to contain a float, minus 1.3, plus 2.7, plus 0.3, some float. We're going to read that value out. And in your robot, that floating point number is interpreted as a desired angle. In this case, we're going to interpret that floating point value as the amount of black to put at that position. So let's assume the amount of black at 0, 0 is 0.5. I put a medium amount of black. Then I go to the next point, which is x equals 0.1. And y equals 0, I take the same neural network, I feed in 0.1 and 0, propagate that through the neural network. Maybe this time a different floating point value arrives at the output neuron, like maybe 0.7, and I put a little more black at that position. The CPPN is telling me how much black to place at each point in this 2D canvas. And if we keep doing that, I keep taking the XY coordinates and plugging it into this one CPPN. That CPPN is going to paint a pattern across the canvas. So far, so good? Okay, how does it do that? It does that by a combination of some familiar things we've seen before, like taking the values in the neurons, multiplying them by a synaptic weight, and adding that to the sum arriving at this neuron. We're going to propagate values through a neural network like we've done many times before. But we're also going to make a little change in this case. You'll notice that in these 1, 2, 3, 4, 5, 6 neurons, there's a little graph inside. Here's the identity function. You can see x equals y in this case. Here's a Gaussian function in here. Here's another Gaussian in here. What do you think these little inset graphs represent? They're sitting inside a neuron. It's a strong hint. What do you think these little graphs are? There's several things about CPPNs that are familiar. We've got a collection of neurons and synapses. The synapses have weights. We're going to flow or propagate values from the input layer to the output layer in the way that we've seen before. What are we missing? What else do we need to complete our neural network? We've got neurons, synapses, synaptic weights, propagation of values forward. The fitness function, true. We haven't talked about a fitness function. We haven't talked about how we're going to evolve populations of CPPNs yet. You're right. We'll come to that in a moment. What are we missing that's specific to neural networks?
These are activations.
Activation functions. It turns out that in a CPPN, we're going to evolve not just the synaptic weights, but we're going to also evolve integers that are sitting in an integer. One integer sits inside every neuron, and that integer indicates which activation function to use for that neuron. An integer of 0 might represent the identity function. An integer of 1 might represent a Gaussian function. An integer of 2 might represent a trigonometric function, which seems kind of odd. We haven't heard that before. Just as a reminder about what an activation function is, let's take this neuron down here, this output neuron. Remember that to compute the value of this neuron, we take the value of this neuron, multiply it by this weight, the value of this neuron, multiply it by this weight, sum these two together. The value of this neuron is this times this, plus this times this, plus this times this, plus this times this. We now have, sitting at this neuron, a weighted sum. We take that weighted sum, which is represented by the x value here, and we push that weighted sum through the activation function, which is represented on the y-axis here. The activation function indicates how to transform that weighted sum into the actual final value of that neuron. So far, so good? Okay. All right, let's try this out now. Let's make a CPPN. I want to make sure that this can be seen by the folks at home. Let me just redraw this a little bit. Let's see how this CPPN operates, which is made up of different neurons that possibly house different activation functions. We've got our two input neurons here that are going to receive x and y coordinates. And let's make this as simple as possible. Let's just have one output neuron, no hidden neurons. Let's keep things really simple. Let's assign a 1 as a weight to both synapses. And let me make this a little bigger. Let's put the identity function inside, the activation function inside. What does the identity function mean? It means whatever the raw weighted sum is that's arriving at this neuron, it's not transformed. The identity function says, leave that weighted sum alone. Don't do anything. Yeah? Okay. All right. So let's see what pattern this CPPN paints onto the canvas. We start with x equals 0, y equals 0. What does this CPPN tell us to do at 0, 0? Nothing. We plug 0, 0 in here. 0 times 1 plus 0 times 1 is 0. The raw weighted sum arriving here is 0. The identity function says leave 0 alone, so it's 0. So I don't put any black at 0, 0. Now I plug in 0.1 and 0. Now I'm considering how much black to put at this position. How much black does this CPPN tell me to paint at this location? Okay, someone's had their caffeine this morning. 0.1 times 1 is 0.1, plus 0 is 0.1, so I put a little bit of black. Okay, one more. 0.2, 0.2, 0. Thank you. Tell me about the rest of this row. There's a gradient. More and more black as we move to the right. What about this row, where y equals 0.1? What gets painted into the second row? We plug this into the network, plug this into the network, plug, 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 plug.
Same gradient, just shifted.
It's a little bit stronger, right? You can do this for yourself. What do we end up getting across this entire canvas? Where's the most black placed? If we go between 0 and 1 on both axes, where does the CPPN tell us to put the most amount of black?
At 1, 1.
At 1, 1 up here, right? So it starts with very darkness here, and then there's some sort of diagonal gradient here. Everybody see that? Okay. Let's try a different CPPN. We're not doing any evolution yet, no fitness function. We're just exercising our intuition about how these CPPNs work. Let's imagine this CPPN, for whatever reason, survives in the population and produces an offspring which is a randomly modified copy of itself, this CPPN. We've made one change. We've just knocked out one of the synaptic weights. What pattern does this child CPPN paint on the canvas?
It'll just be the same gradient at each y value that's initial one we had.
Absolutely. It's going to be the same horizontal gradient at every point. It's going to look the same at every value of y because y does not influence what the CPPN generates. Everybody see that? Okay, so we just saw one parent CPPN that painted a gradient in this way. We now saw another child that paints a different type of gradient, this way. What about this child? Assuming the parent produced a second child, which is this child, what pattern does this CPPN paint?
Just like a gradient from the bottom to the top.
A gradient from the bottom to the top. Yeah, sure. Yeah, it starts white and gets darker and darker and darker as we travel up. We've just simulated 3 different CPPNs where I made some random changes, and each of the 3 CPPNs produced a regular pattern. They produced a gradation. What any of these CPPNs did not do is produce white noise, some random pattern, some random speckling of white, gray, and black across the canvas that has no discernible pattern to it. We're short on time, so I invite you to try and create other CPPNs, and you'll find that the vast majority of them tend to produce regular patterns like gradations. I mentioned sometimes a CPPN will have a different activation function inside, like a trigonometric function. What do you think a CPPN with a trigonometric function does? What kind of pattern might that produce? Let's take this relatively simple CPPN. Yep.
Like stripes, maybe?
Stripes, exactly, right? So you can simulate this yourself. Put the sine function in here. Compute the y value, which goes in here and dictates as you travel up, as this value gets larger and larger as you travel up, sometimes that value of y hits a high value and you place a stripe. Sometimes it hits a lower value and you'll get horizontal stripes. Yeah. So we're making changes to the CPPN. You can imagine these as mutations. We're mutating or changing weights when children are produced from parents. We can mutate a CPP in HyperNEAT. We are going to evolve or mutate activation functions inside. And as we do, as we have a population of evolving CPPNs, they tend to paint regular patterns that have gradations, stripes, symmetry. So you'll notice the Gaussian function over here. If you look at the shape of the Gaussian curve, it looks the same on its left as it does on its right. So what is this little cartoon fly representing? It's representing that, like in nature, this particular genome, this set of synaptic weights plus set of activation functions, that specifies a phenotype, which in HyperNEAT, the phenotype is the pattern produced by this thing, phenotypes with regular structure in them. Everybody see that? Okay. This has nothing to do with robots yet, has nothing to do with even evolution. We haven't started evolving things yet. Let's continue to build up our intuition for CPPNs. In this case, we've been painting patterns across a two-dimensional canvas. What might happen if we wanted a CPPN to paint regular patterns within a three-dimensional volume? How might you have to change the genome to produce three-dimensional phenotypes? We want to paint a regular pattern now inside a box. What do we need to change about the CPPN?
3 input neurons.
Sorry?
3 input neurons.
Exactly. Now we would visit a whole bunch of positions inside this three-dimensional cube, place those 3D coordinates in here, and the CPPN would tell us what to do at that position. At the moment, we have just one output neuron, and we've chosen to interpret the value at the output neuron as the amount of black. Okay, let's go back to 2D for a moment. Let's go back to 2D for a moment. The cartoon here you can see is not in black and white, it's in color. How would we alter our CPPN so that it paints in color rather than grayscale?
Add RGB.
Now we have 3 output neurons, R, G, B. If we took this exact CPPN that I have drawn on the board right now, it's only going to paint it with green. But if this parent survives and perhaps a synapse gets added through mutation, now it's painting in color. You can try this if you're a comfortable programmer, you can sit down with Python and Matplotlib. You can create some CPPNs at random, no evolution, just create random networks and have them paint patterns and convince yourself that these kinds of neural networks, even if you wire them up randomly, they tend to produce non-random patterns. Yeah? Like NEAT, HyperNEAT is a very popular algorithm. It's been used for a lot of different things. It's been used in the art world to produce interesting and beautiful patterns in 2D and 3D. Turns out you can also get CPPNs that will not just paint images, they'll paint movies or animations. How? What change do we need to make now to have a single CPPN produce a movie or an animation, a moving pattern?
Backpropagation to keep running over and over again?
Close. So we need to evaluate the CPPN many times, not back propagation, but we need to do forward propagation. So we take our 2D canvas, and whatever our CPPN is, it paints a pattern in now the first frame of the movie. Now we need the same CPPN to paint a second frame. We could just give it a fresh canvas, but it'll paint exactly the same pattern onto that second frame. So we're going to get a movie in which nothing changes. Not kind of what we want. How do we need to alter the architecture of a CPPN so that now it's painting patterns that change in time?
Do you alter the synaptic weights?
We could. So we could ask it to paint a picture and then slightly alter the synaptic weights, and now it'll paint a second canvas. And if you change the weights only a little bit, that'll alter the pattern a little bit on the second canvas and rinse and repeat. Great idea. But now we need, if we have 1,000 frames in our video, we need 1,000 sets of synapses. That's going to be a very, 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 very long genome, thousands or millions of synaptic weights long. Good, but a little cumbersome for evolution to evolve. Is there another way we can alter the neural architecture of a CPPN so that it'll paint a moving picture?
Different inputs.
Different inputs. What do we need to change about the inputs?
What's the values of?
So this is the thing that's most unique about a CPPN. We're feeding in coordinates. We're feeding in positions in space. For now, strong hint. Did you have an idea?
Yeah, we need to have time as an input variable.
Time, or the index of the frame, right? So if there are synapses flowing out from our temporal neuron now, we're going to tell it, paint a particular pattern onto frame 0. Now paint a pattern onto frame 1. Now paint a pattern onto frame 2, and so on. If we're incrementing over integers, that's a big jump from 0 to 1 to 2. We might get a big change in whatever the pattern is. So typically, when CPPNs are used to generate animations, we start with 0, and then the next time index is 0.01, 02, 03. The smaller the distance between the temporal or time indices, the less the pattern changes from one frame to the next. Everybody see that? You can probably see now why HyperNEAT was one of the very first generative AI algorithms. By making changes to the neural architecture of CPPNs, you can get it to generate different kinds of things. And regardless of whether it's generating things in 2 dimensions, 3 dimensions, over time, in black and white, in color, wiring them up randomly tends to produce non-random and in some cases very beautiful and engaging pictures and animations. Used quite a bit in the art world still to this day. Any music aficionados here? You can also take an empty music sheet, and on a musical sheet at different bars, and staves, and I don't know my music lingo very well, at different locations, placing things at those points means something musically. You can walk across a blank page, a blank sheet of music, and get your CPPN to paint or not paint a note at that location and at that time. And by doing that, you can get a CPPN to generate music. And it turns out it's not that terrible music, because CPPNs don't paint a random collection of notes across the sheet of music. It tends to produce regular patterns at different places on the sheet of music, which tends for most people to produce something that's not too terrible to listen to. Turns out in the early days of bioinformatics, the bringing together of computer science and genetics, people also used used CPPNs to paint amino acids along a one-dimensional line to create new kind of prospective proteins and ultimately medicines. A lot of the things that you're made up of and the things that you ingest or digest to keep you alive are also not random collections of things. So far, so good? Okay, that's HyperNEAT. Got nothing, those are CPPNs. They have nothing to do with robots yet. So let's now take a population of random CPPNs and wrap it in an evolutionary algorithm. An evolutionary algorithm that's going to evolve populations of different CPPNs, each of which paints its own unique non-random pattern. And we're going to evolve those CPPNs where we're going to evaluate the pattern, whatever it is that they produce, against a fitness function. That gives us HyperNEAT. We're going to wrap NEAT around a population of CPPNs. And remember that the NEAT algorithm just evolves populations of neural networks. The NEAT algorithm doesn't care what those neural networks do, it just evolves them. That's the HyperNEAT algorithm. Okay, so if we're going to evolve populations of CPPNs, we need to have some way to take the phenotype, which in this case is the pattern, and assign a fitness value to it. How good or how bad is that pattern? If we're using this to generate art, that's very difficult to do because the aesthetic quality of a given pattern is subjective. You might give it an F of 0, you might give it an F of infinity. It's the best, most beautiful picture you've ever seen. Kind of subjective. Okay, so we're going to look at this particular experiment down here, which used HyperNEAT to evolve controllers for robots. What is the intuition here? We're going to try and they are going to try and evolve populations of CPPNs, which are neural networks. That's the G, the CPPN. That CPPN is not going to paint colors onto a canvas. It's going to paint weights onto a set of synapses. So this experiment is a little confusing because there are two neural networks in play. The first neural network is the CPPN. The second neural network has a whole bunch of synapses in it that don't have any weights assigned to it. We're going to visit each unweighted synapse in this second neural network. We're going to give the coordinates of that synapse, where that synapse exists in space. We're going to give those coordinates to the CPPN, and the CPPN, the floating point value that arrives at the one and only one output neuron, is the weight of that synapse. We're going to paint, or the CPPN is going to paint a regular pattern of synaptic weights across the second neural network, which is going to control a robot. A lot of moving pieces in this experiment. We'll see how it does that in a moment, but I want to make sure you've got all the basic pieces in your head. Yeah? Okay, so we have a population of CPPNs. At the beginning of evolution, we take the first random CPPN. It paints weights onto the neural network controller of a robot. We take that robot, put it in a physics engine, let it do its thing for 1,000 time steps, and compute the fitness of that robot. How far does it move to the right? We're going to evolve the exact same fitness function that you're using in assignment 10 for a quadruped. Not that different, but we've got a much more complicated evolutionary algorithm now. And the reason why we're going to all this extra effort is based on the assumption that brains of robots, like your brain, will produce more regular patterns of locomotion if the brain of the robot itself has a regular pattern of synaptic weights across it. That's the hypothesis. We're going to see if that's correct. So far, so good? Okay, let's see how they did this. If we're going to have a CPPN paint weights onto synapses, those synapses have to have positions in space because that's how the CPPN works. It needs a position. It needs a set of coordinates. So here's the neural network controller for the quadruped I just showed you. And this neural network controller, as shown here, is embedded in three-dimensional space. All of the neural networks we've seen in this course so far, they're drawn spatially. There's a picture, you can draw a picture of them, but it's not really like this hidden neuron exists to the left of this hidden neuron. In this neural network, that's literally true. This sensor neuron here is to the left of this sensor neuron. This motor neuron here is further along the y-axis than this sensor neuron here. So here's the x-axis, here's the y-axis, and here's the z-axis. So we are embedding all the neurons represented by the circles here in three-dimensional space. So far, so good? Okay. They have not drawn all of the synapses here because this thing would be an absolute mess if they did. So I'll just tell you how this is wired up. We have 1, 2, 3, 4, 5 times 1, 2, 3, 4. We have 20 sensor neurons. Each and every one of these 20 sensor neurons sends out a synapse that connects to each and every one of the 20 hidden neurons. We have 20 sensor neurons. embedded in a 2D plane. We have a second set of 20 hidden neurons embedded in a second two-dimensional plane, and it's fully connected. Every sensor neuron here connects to each and every one of the 20 hidden neurons. Each hidden neuron connects to each and every one of the 1, 2, 3 times 1, 2, 3, 4. 3 times 4 is 12. Each hidden neuron connects to each and every one of the 12 motor neurons. Okay, so we've got 20 sensor neurons, 20 hidden neurons, 12 motor neurons, and these 12 motor neurons send desired angles to the 12 motors that make up this robot. You'll notice that it's a quadruped. Each of the 4 legs has 3 motorized joints inside of it. 1 knee and 2 and 3 motors at the hip. 2 motors at the hip and a third one at the knee. 3 motors per leg. 4 legs gives us 12 motor neurons. So you'll notice there's 4 rows of 3. Each row here corresponds to each of the 4 legs. This is the motor neuron for the knee in the first leg. And here's this motor neuron is for the first of the 2 motors in the hip of the first leg. And this motor neuron controls the second rotational joint in the hip of the first leg, and so on. So far, so good? Everybody seeing how this works? Okay, so that's the motor neurons, hidden neurons. Let's talk about the input layer here. We've got 20 sensor neurons. Again, we've got 4 rows here, legs 1, 2, 3, and 4. And we see the columns here are labeled with hip forward and backwards, hip in and out. These 3 times 4, the 12 neurons in here, these are proprioceptive sensors or angle sensors. They're reporting the current angle of the forward and back hip in leg 1. This proprioceptive sensor is reporting the current angle of the inward and outward motor of the hip. And this motor neuron is reporting the current angle of the knee in the first leg. So we've got 12 proprioceptive sensors that are sending in values at every time step of the simulation. We've got 4 binary touch sensors, 1 at the bottom of each of the 4 feet. And then finally, we've got a miscellaneous collection of input neurons over here. We've got 3 neurons here that report the pitch of the torso, how much the torso is pitched forward or pitched back, how much the torso is rolling about its long axis, and then finally, how much the torso is yawing about the vertical axis. So these 3 numbers, we talked about this last class, I think. This is the inner ear of the robot. These 3 neurons together report the orientation of the torso relative to the ground. And then finally, the 20th sensor neuron here is outputting a sinusoidal pattern. Where have we heard that before? You have some of these in your spine. The chicken that unfortunately gets its head cut off also has some of these in its spine.
These are your, what are they, central pattern generators?
Perfect. Central pattern generators. For rhythmic motion, it tends to be useful to have a bit of a conductor who's outputting a certain frequency or cadence at which you should move, and all these other sensors are helping you modulate or clean up that gait, that regular pattern, as you move across the irregular patterns in your environment. So far, so good? Okay. So now we got to figure out, this is the neural network controller for the robot. Imagine we have a CPPN that has one and only one. Let me draw this a little bit to clear this up again. We have a CPPN that's going to try and paint synaptic weights onto this thing. So far, what we know about the CPPN is there's one and only one output neuron, which is going to be the weight of a given synapse. We now need to visit each and every synapse that connects either an input neuron to a hidden neuron or a hidden neuron to an output neuron. And we're going to give the CPPN the coordinates of that synapse, and it'll give us back the weight for that synapse. How are we going to construct the input layer for this CPPN?
You could use X, Y, and Z.
Let's try it. Let's assume that we're going to give the X, Y, and Z of the synapse. The synapse is a line, so it doesn't have just one X, Y, Z. Which X, Y, Z?
Of like these three layers. So like the X or Y would be like 1, 2, 3.
Okay. Okay, we could do that. So we could say which layer. Let's do that.
Yeah.
Okay. So this is going to be an integer, 0, 1, or 2.
Right. And then the X, it's not going to be 5 all the way because it only has 3 in the last one. But
Okay. So we're going to use an integer encoding. We could do this.
yeah,
Okay.
all integers.
Got it. Okay. So 0, 1, or 2 is going to represent which of these 3 sheets to visit. X and Z could be the row and column, I guess.
Yeah.
Okay, we could do that. So all of these, I'll just put I for integer. Okay, we could do that. It sounds to me like that's a little bit more of the location of the neurons, right? So sheet 0, row 0, column 0 is this position. Did I get your encoding correct, or am I missing something?
Yeah.
Okay. We're looking not for the positions of the neurons, but we're trying to get positions of synapses that start at a particular neuron and go to another neuron. Everybody see that? So if we use the integers, that's going to give us a location within one of the sheets. It's going to give a position for a neuron. But for this neuron, for example, in sheet 0, row 0, column 0, there are actually 20 synapses coming out of this neuron, attaching to each of the 20 hidden neurons here. So we don't yet have an address system that will uniquely identify each and every synapse in this three-dimensional space.
Could you use like early coordinates? So like from one sheet to the next?
Now we're getting somewhere. Okay, so let's assume there are actually 6 neurons at the input layer. X, Y, and Z of the presynaptic neuron's position. So we can use your integer encoding. So for example, let's assume we put in 0, 0, 0 here. We're starting to tell the CPPN we want to paint a weight onto one of the synapses that starts here, and maybe we're trying to paint a weight onto the synapse that goes from here to here. So this is sheet 1. Sheet 1, row 0, and column 1. Here's column 0, column 1. So this could be the X, Y, and Z coordinates of the postsynaptic neuron. We're going to specify the address for a given synapse inside this thing using 6 numbers. Everybody see that? Okay. If we do, we're unique. This is a good encoding because we're uniquely identifying each and every synapse in here. We can walk across the, I don't know how many synapses there are in here. There's probably 100 or so. Each of those has a unique address, which means we're going to get possibly a unique number down here. We can now paint any given CPPN. I haven't shown the connections here, but you could imagine something like this. There's no hidden neurons here, but we could have some. So now we can now paint, or this CPPN can paint a weight onto each and every synapse in this neural network. Everybody see that? I see a lot of folks squinting. That's okay. There's a lot going on here. We have a robot that exists in 3 dimensions. It exists in 3 dimensions in the physics engine. Its brain exists in 3 dimensions. We're embedding all of the neurons in 3-dimensional space. From the perspective of the CPPN, it's painting a regular pattern. It doesn't know what W is, it's just spitting out numbers. It's painting a regular pattern across 6 dimensions from its perspective. Everybody see that? Okay, it's a little confusing, but imagine we could do that. We're almost all the way there now. Imagine we have a population. We have a population of these things. We have a whole bunch of different CPPNs. They're being evolved by HyperNEAT, so some of them may have different internal structure, but they all have 6 input neurons and 1 output neuron. Each one of those random CPPNs in the initial population paints a different distribution of weights across this thing, across the neural network controller. We take each of those neural network controllers. If we have a population size of 13, we have 13 CPPNs. Each CPPN paints a neural network controller. So we have now 13 unique neural network controllers. We drop each one into the virtual robot. We run 13 simulations. We allow those 13 controllers to control each virtual robot. Some are going to travel further to the right than others. We delete the ones that don't travel so far, and we make randomly modified copies of these things as offspring. I notice a few furrowed brows and squints. Something still not clear? Anything I can clarify? Question?
Wouldn't you need another 3 neurons in the input layer to do the synapses from the hidden to the output?
So from the hidden, let's do the hidden to the output. So if we're going to use your integer encoding scheme, which is a good one. So sorry, we're using y as our index into the sheet. So if we want to label, for example, this synapse that starts here and goes here, I'm going to do this synapse. The presynaptic neuron is here. It's in sheet 1. And we're saying that we want the weight for the synapse that starts in sheet 1 and ends in sheet 2.
Yeah.
Got it? So this encoding, your 2 ideas put together produce something that can uniquely identify every synapse, no matter where it is. Okay, let's make sure we're really wrapping our heads, no pun intended, around this idea. I haven't mentioned anything about recurrent or self-connections yet. I've only said there's synapses going from input to hidden and from hidden to output. Let's assume for fun that there are recurrent and hidden connections. Does this way of encoding coordinates of the synapses still work? Do we need to add anything? Can we still uniquely identify recurrent and self connections? You're nodding. Why?
Well, because it's a pre to post synapse. Like it still like traces a path.
It still traces a path. So if we start with this set of coordinates, we're asking for the weight. We're asking for the weight of a synapse that starts in layer 1 and ends in layer 1. Imagine this hidden neuron here, which is in row 0, column 0. Row 0, column 0. Let's assume that that is a self connection. It's a self synapse. It leaves 0, 1, 0, which is this neuron, and arrives at neuron 0, 1, 0. That's a self connection. This is still a unique address in this system. So we could add recurrent and self connections, and this approach would still work. Okay, let's pull back. We're evolving populations of neural networks. Each one of these neural networks paints weights onto a neural network that exists in 3 dimensions. It's from the first neural network's perspective, it's painting a pattern in 6-dimensional space, but it gives us in the end a whole bunch of weights across the neural network controller, and we can evaluate each robot to see how it works. Okay, I'm going to just back up for a moment. And we're going to talk about the fourth and final part of the acronym of CPPN. So hopefully you all are now convinced that these networks produce patterns. How do they do it? They're doing it through coordinate compositions. We give it a coordinate system. The coordinate system we just saw exists in 6-dimensional space. When we start to pass that coordinate down through the neural network, that neural network does what every other neural network does. It starts to transform its input into output. It's transforming the coordinates and composing it with other transformations as it goes. It's rotating, compressing, stretching, repeating. It's doing some coordinate compositions along the way. If coordinate composition sounds unfamiliar to you, that's okay. You can look into it. That's how the CPPN is doing what it does. Okay. All right, we're reaching almost the end of this very long lecture. So let's see how it does. All of this machinery has been built on an idea, which may or may not be true. The idea is that if you have regular patterns of weights in your brain, you're going to tend to move or behave with a regular pattern more than something else that might have exactly the same neural architecture, but a random wiring up of synaptic weights. So the experimenters tested this hypothesis by evolving the CPPNs we just talked about in exactly the way we just said. That's the experiment called HyperNEAT. They then ran a control algorithm. This is like the A/B testing we talked about last time. They ran a control experiment, which is exactly the same as before, but they're now going to remove the CPPNs. They're just going to evolve sets of synaptic weights using NEAT. So there is no longer in FT-NEAT, they get rid of the CPPNs, and they're just evolving populations of these things using NEAT. So they've dropped the thing that tends to paint regular patterns. So far, so good. Why is it called FT-NEAT? The FT stands for fixed topology. Remember that the NEAT algorithm, if we go all the way back here, the NEAT algorithm can add and remove neurons and synapses. They turn that part of NEAT off because we have a fixed topology. This is it. These are the neurons and synapses. Evolution is not allowed to add or remove anything. That's why it's called FT-NEAT. So they're going to evolve populations of this thing, same fitness function, same evolutionary algorithm, same everything else. Let's see what happens. This is the best controller that was evolved by FT-NEAT. If we just directly evolve sets of synaptic weights, like you're more or less like you're doing in assignment 10, this is what you get. How's the robot doing? There's a bit of a regular gait here. We're still kind of in the ministry of silly walks. There's a little bit of bouncing around. But after hours and hours and hours of running this evolutionary algorithm, they started to get some regular locomotion in their quadruped. That's FT-NEAT, the control experiment. Let's go back to HyperNEAT, where now we're evolving CPPNs. This is what they got. Much, much cleaner, much more efficient. Okay, so what have we just seen? We've seen two evolutionary algorithms that are searching over the space of all possible brains for this thing. But this algorithm, HyperNEAT, is being forced to search a subset of that vast space. It's being forced to focus on regular distributions of synaptic weights across the brain of the robot, and that allows that evolutionary algorithm, HyperNEAT, to very quickly find very clean, regular modes of locomotion. Okay, we did it. We got to the end of lecture 13. Next time, we'll start talking about the reality gap. You have a quiz due tonight, and you're working on ideas for your final project. Have a great rest of your week.